In this video, we're going to discuss some of the changes that have happened to Earth, how they came about, how it changed the concentration and form of various elements, and how that's affected our modern world. Here on the left, I have a graph of atmospheric oxygen pressure versus billions of years. Life began, we estimate, around 3.8 billion years ago. Some new evidence says it might be a little further out, but this is where we have some good hard evidence for. For about the first 1.3 billion years, there was almost no atmospheric oxygen. Majority of the atmosphere was methane, there may have been some ammonia, plenty of nitrogen, and some carbon dioxide. But by and large, there was almost no oxygen in the atmosphere. So the early atmosphere of the Earth, we believe, was a reducing environment. And life that evolved at this time was built for an environment where available reductants were plentiful. But then the great oxygenation event occurred. Somewhere in around 2.8-ish billion years ago, maybe 2.5-ish, something emerged that starts producing oxygen. Cyanobacteria are what we believe is the cause of this, and for a while, it wasn't a whole lot. But it did grow over time. Earth's oceans had been largely filled with iron 2 type compounds. As oxygen began to show up more and more, those ions began to react with it. And so we started seeing iron 3 compounds and iron 3 oxide. And it even started forming a little bit earlier, and it was consuming this oxygen. But at some point, most of that available source to dump the oxygen got used up. And so we saw oxygen begin to increase. Now we start to see some O2 show up. During this time, we also see less methane. So we see some CO2, we see N2s, and a little bit of O2s. As O2 forms, it reacts with methane over time to have our atmosphere to form more CO2. And so the methane began to disappear. We actually had cooling events. The first snowball Earth occurred because the methane went away and we were still too far from the sun back then. The sun gets warmer over time. As it expands, it gets a larger photosphere, emits more of the light that's generating out to the rest of the universe. And so the Earth, at the time, had a much dimmer star. Without that methane helping the greenhouse gas, it began to freeze. We're not exactly sure how much of the planet really froze. Estimates are from all of it to almost all of it. Life did seem to survive over time. CO2 built up from other sources, filled in for the methane difference. The planet got a little hotter from more sunlight, and eventually the ice melted. Life continued to flourish, and oxygen remained largely stable for a while. There was a balance of it with the various organisms that made it and then consumed it, and then suddenly it spiked. About the time land life started showing up, we see it truly spike. So in the Cenozoic era, as plants began to grow on land, there was a new field of area where we could have something consume carbon dioxide. But when plants consumed carbon dioxide, they produced oxygen as well in huge quantities. Because the early forms were small, it only increased so much. But eventually, around 350 million years ago, the scale trees showed up. Here we see an artist's rendition based on fossils for some of the look of them. These were towering trees that would shoot up in incredibly short periods of time, branch out, and we think they lived for one breeding cycle and then fell. And they had very weak root systems, so the winds would blast them over and tip them. But these were the first plants that could grow really tall, things we would think of as trees. While cellulose existed for all plants, lignin, which binds cellulose tightly and makes them tougher material that we think of for trees, that was a new evolutionary development. As a result, these could get much taller than all the other ferns and the like that existed at the time, getting way up above to get more sunlight, to get more wind, to spread the seeds and get further. These were a very successful species. And for about 50 to 60 million years, These would grow, fall, and not decay. Nothing had evolved to eat lignin yet, and the cellulose bound up in it. So as these fell over and died from no longer getting sunlight, the tree's carcass, the trunk and everything remained. And a new generation would grow up and fall and squish it, and a new generation would grow up and fall and squish it, and bit by bit, these compressed. But the carbon trapped in them stayed trapped in them. They weren't cycling. This is why we say massive increase in oxygen in this period. Every time a sugar was produced to make one of these trees, it would free up some oxygens into the atmosphere, and then the tree would fall, trapping that carbon and not bringing that oxygen back to it. So oxygen spiked in the atmosphere and carbon piled up on the ground. Well, imagine you have some big valley, and you have lots of these little trees grow over time, and then they fall. And then more grow, and then they fall, and then more grow, and they fall. And this just keeps happening, and little bits of dirt fill in, things grow on top. And over the eons, entire valley growth fields would be compressed down and filled with these trees to eventually become coal. Almost the entirety of the coal supply of the planet is actually crushed scale trees. This removed an enormous amount of carbon from the atmosphere. Actually brought about a little bit of ice age again. Earth's been cycling ice ages due to the interactions of carbon and oxygen and the creatures that consume and produce them, ever since that showed up. But this is where almost all the coal on the planet came from and the cause of the rise of oxygen in the Cenozoic period. Today we're hanging around 20% oxygen, as things can now consume lignin. Various fungus and the like developed the means to do it, and so bark and trees do break down over time. This is a problem with trying to remove carbon from the atmosphere. As we're breaking up and burning coal to produce more CO2, even if we grow trees, those trees don't trap it. That CO2 is just permanently free in our atmosphere now. We would have to grow an enormous amount of forest and leave them there so that the weights of the forest balanced out the amount of CO2 we've released from the coal, and, well, given our farmland demands, that's not particularly likely. So unless we can trap our CO2 in some other fashion, planting trees is not really going to be able to counteract global warming. It's a tool, but it's not the answer. But here's where we've gotten some of our materials. Things that power our world around us today, and the very air we breathe at the level of oxygenation that we have presently that we need to survive. So here's a few changes that have occurred to Earth just through life's effect on it. Well, these aren't the only changes that occurred to Earth. When we think about the planet and its various layers, early on Earth was completely molten. Heavier elements all sank further down, stratified themselves throughout the layers based on their densities. And it's actually believed that early on, a lot of the elements like phosphorus and sulfur pretty much left the crust, sank further into the planet. So much so that there would be very, very little of it available on the crust. But there's actually a reasonable amount of them, more than some of our estimations think should be there. One of the explanations for this is just after Earth started to cool, we believe we got hit by an object about the size of Mars. So early on in the existence, way out here, for some billion years ago, there was a massive stellar collision. Two objects around the sun, pre-Earth, and some other objects slammed into each other and actually broke a huge chunk of the planet off and mixed up a great deal of the inside layers. Additionally, this other object brought its own material. And the planet was close enough that as it started to cool again, it cooled pretty quickly. Enough time that it didn't have the hundreds of millions of years to fully separate out those elements. And so a lot of heavier elements got left up near the crust from this collision from this other stellar body. And so we actually have a higher percentage of sulfur and phosphorus than some of our estimates think we should in the crust layers. This also formed the moon. Lots of debris from that collision coalesced and we believe formed the moon around our planet. Additionally, it probably disrupted enough of the surface that it led to the separate plates. Instead of having one smooth crust all over, we have a large number of broken continental plates that drift around. This may have happened naturally on its own. We don't have a lot of bodies to compare to, but there's a lot of thought that it might not have. And that subduction is vital for the regeneration of things like phosphates and nitrogen and other things through the elemental cycles of our planet. And so that early impact may have been vital for all the things that maintain life on the surface to this day. So there's a lot of complex interactions that have changed our planet over time that led to the present distributions of various materials that we find. Not all of them are quickly obvious, some of them are theoretical, and some, just recently, got some better evidence. And we actually think we found chunks of the other object still intact inside the mantle. There's a research paper that showed that there's some mountains effectively in the mantle drifting around, and they appear to be differently constructed than the other mantle around it. If this is true, and they're continuing to map more and more to see, it may be chunks of the other stellar body that remained largely intact, merged into the molten planet upon impact, and is now locked inside our Earth.